Okay, so thanks everyone for coming to the TDNeuron workshop. I am Darien, and this is Tim. We will introduce each other a little bit first, and then we will describe what we're going to see, and then we start right away. So my background is on music, actually, and I slowly went into TouchDesigner and computer graphics, and developed this interest in machine learning now. And yeah, it has been a very experimental journey so far. And we partnered to do this because of this reason. So that's more or less my background.
So, hello, I'm Tim. My background is more in software developing. And I'm very in love with TouchDesigner now. And a big hobby of mine is artificial intelligence and learning a little bit about how it works. And hopefully today we can show you a little bit about what it is and what, how it works a little bit. To start with, I'm going to show you a little model we made just to describe what you can do with machine learning. This is a leap motion. Maybe you all know about it. It records like the positions of your hand. And what we did is it finds the gestures. We train it on just numbers. So it finds like how many fingers you hold up. And normally you can do this with just programming, like, okay, if this finger is pointing that way, it's a 1 and stuff like this. But instead, what we did is train our hand, train a lot of movements by just showing the computer how it's done, and then it will recognize what we're doing. So yeah. Hopefully, in the end of the workshop, you all know how to build something like this, or with a Kinect or other devices you can use, stuff like this. So yeah.
Then I gotta get this. All right. So I'm going to give you a very brief history of machine learning and how it evolved and why it's in the state that it is at the moment. So, all right. Okay, so this one is a Blaise Pascal calculator that was in 1642. And he built this for his father, who was a banker. So it was just to calculate simple transactions. This one is the design made by Charles Babbage from the analytical engine, and this was from 1832. And this is the design of the first computer that was ever made, like the first formalized version of a computer ever made. Then we have Ada Lovelace, who is incidentally the first programmer. So the first programmer was a woman, and she was very much in contact with Charles Babbage, and this was in 1840. Then we have Alan Turing, who was the father of computer science, and his most influential paper for this topic was on computable numbers, which is very interesting to read if you want to check it out. And this was in 1936. Then we have in 1958, so that's like over 60 years ago, the Rosenblatt perceptron. So this was developed as the prototype of a neural network. So it's a perceptron with one single neuron, and it's already from 1958, so quite early. This one is the Motherline neural network, and it's from 1959, and it's a denoiser. So what it does, it takes out the noise from phone signals. So as you see, again, very early, 1959. But we can already see here components that are part of the modern neural networks that we're going to build. So then we have the NetTalk, which is a speech synthesizer from 1985. After only 1 week of training, it was able to say 20,000 words correctly. Then we have Garry Kasparov against Deep Blue. This is in 1991. And this is a very interesting trend in machine learning, which is to test the systems against games, because games are ideal to test it since they have simple rules. that you can define formally, and because they involve creativity. So you start to develop certain form of intelligence if you manage to be creative in some way. And yeah, in '91, it was a shock for everyone that machines could defeat the best chess player in the world. Then we have in 2006, so that's, there was this period that nothing much was happening. And in 2006, we have Geoffrey Hinton. And he updated the research of machine learning and AI in general to focus on deep learning. And deep learning, you will understand why it's called deep in a second. Then this is a cat, if you cannot recognize it. And this is from 2012. So Google developed this neural network that could recognize faces of cats and humans. This is Eugene Goostman. Is the first chatbot to pass the Turing test. I don't know if you're familiar with the Turing test. Yeah, everyone is familiar with it. So it's the first chatbot to do it. It fooled 33% of the participants. And it was supposed to be a 12-year-old Ukrainian boy. All right, this is Ian Goodfellow. He's a superstar now. He's the inventor of the GANs, generative adversarial networks. And this was in 2014. Now, from 2014 onwards, there's a huge explosion of AI in many, many different fields. And it's partly thanks to this guy. OK, then we have AlphaGo. AlphaGo, again, is an attempt to take a game and test it against a computer to see how well it performs. And it's the first time a computer could defeat a professional Go player. And this was a big shock for all the AI community because it means that machines got so good at develop some form of intelligence that could defeat it in the hardest game that humans have ever created. And this is in 2016. All right, this is from 2018. This is Weimar Alphabet, which is the subsidiary company from Google, is the first already commercially available self-driving car. And it's been tested now with 400 people. And it's already functioning. And finally, we have two more examples. 2018, this is generative portraits. So none of those faces are real. Those are synthesized faces. And this is by NVIDIA. They made this research. And finally, yet again with another game, we have in 2018 AlphaStar. AlphaStar is this AI that defeated the best player of StarCraft 2. And this is the current state, more or less. Of course, it's a very flashy history of AI, and I encourage you to research more. But to give you the idea that machines are tested against rules and creativity. All right? Then, what is machine learning at its core? So if you dive into the second section, so that's, sorry, section 001. Oh, yeah. I think it's missing the USB. He's missing some files, I think. Yeah. So here we see the programming approach. All right, so in this section we see the programming approach, which is that typically when we are programming we have an input. We're going to call it that input X. Then we have the program, and within the program we make operations with that input. So in this case of this very simple program is a math operation. We're multiplying the input by some number, in this case 2, and this goes out to an output. So the programming approach is very much linear in the sense that we give a set of instructions to get an expected output. However, when we take the machine learning approach, we are going to do it differently. So we have also an input, but instead of telling the computer what operation and what parameter it should use for this operation, we're going to give it just the rules for the operation. So some ground truth or some set of rules that it should learn. And this is a condition that it should meet. And in this case, we have the operation done, but we are testing it against some form of error. And we're going to call that the cost. So we're comparing how well the machine is doing with some random, at the beginning, random value, and slowly move the operation so that the cost gets as close as possible to zero. So as you see, we are not, like before, developing a program from one step to the next with an expected output. We're developing a program that learns it, that finds out the right values by itself, based on a cost. And we call that value a prediction. So these are very important elements. I'm going to repeat them once more. We have the inputs. We have a ground truth, which is the known value that we want to achieve, or the known truth. We have a prediction, which is the prediction from the model. And we have a cost, which is the thing that the model uses to compare how well it's doing against the ground truth that we know. All right? OK, so once we learn something, that's called a model. And it's called a model because it doesn't change anymore. And the cool thing about machine learning is that after we have learned the model, we don't need to train it anymore. Once it's learned, we can just use it. So we can take this model and just plug an input with some parameters that were learned in this process, and then it will give us straight away the answer. So we don't need to retrain it. And that's why it's called a model. Now, before Tim takes over, I wanted to ask quickly if any of you read the material we sent online. Someone read? All right. 2 of you? OK. OK, no worries. We'll try to explain everything the best we can. So now Tim takes over to explain you with chops.
All right. Put this here. So why machine learning? Because, the example we just show is very easy to program, and it has no use to really use machine learning for this. Multiplying against something is quite easy. But there are other problems that can be a little bit tricky to program, such as detecting if it's a banana or not. Like if you have an input, the input here is a banana, and we want to see if this is a banana or not. In this case, with a simple program that checks the difference between the input and the ground truth, the eventually goal of the model. We just check the difference of the image. Oh. Then we analyze the pixel color and see if the pixel color is higher or lower than a threshold. As you can see, right now it thinks it's a banana. But if we, for example, rotate it a little bit, then already it says, no, it's not a banana. Yet it is a banana. So that's not a very good program to detect if it's a banana or not. A different kind of approach would be, for example, to first check the average color of the banana and compare that. And if we compare it, then yeah, it's the same color. So yes, it's a banana. But again, if you, for example, put in some noise, it still thinks it's a banana, even though it's totally different colors, totally different form, and it maybe looks like a banana, but it's not really. And what happens is because, it takes the color, it takes the length of the color, so it calculates one number of this color, and, well, it's close to each other, so it thinks it's a banana. So also not a very good way to detect if it's a banana or not. And then you can continue and make it more and more complex. For example, here, to cut out exactly where the banana is, find the color there, and it's a little bit better. But like this, it doesn't say it's a banana. But if we go back to the banana, and we, for example, scale it a bit, maybe rotate it, yeah. As you can see, it still thinks it's not a banana. So just the point is, it's very hard to build a program that really detects if it's a banana or not. And a problem like this is perfectly for machine learning. because it can figure out what's the best pattern to see if it's a banana or not. So to describe how to build such a thing, we start simple. We start with a line. For example, a line, just a line, the math equation of a line is this. Y is ax plus b, where a is the direction of the line, the slope, and b is the offset of the origin. There are some custom parameters here. If you play around with it, you can see like if you change a, it changes the direction. If you change b, it goes up and down. Here's the same thing in chop. So it's just a math multiply and an add. And now the idea is if we have a lot of x's and a lot of y's, so we have a lot of input and we know the output, the y's, there is a way to find the a and the b. So you don't know which direction the line is. So, if you had a lot of data, such as this, and you know where the data is, which is the x, and you know the color, which is the y, there is a line to form where we can exactly classify the difference between red and green, such as that the line would be like something like this. Well, closely like that. So those numbers we can learn. We can train the model to find those two numbers without saying anything, without trying what we just did, but let the computer do it. So how do we do this? First in chops, again, similar like before, a lot of input, multiple samples this time. So we have 10 different input samples, different axes. We start with just random W's and B. Here the W is the pointing to the A, so W is A here. And why is W? It's called a weight, because it's kind of a weighted sum of X. So how much of X is part of the result? B is called a bias. How much is it biased towards positive or negative? So it comes down to like this is exactly the same we did here. This is W and this is B, bias. So if we look at this, we do exactly the same here again. The input times the W, add B, the bias, and that ends up to be our prediction. Now it forms like some kind of data, some kind of line, and now we have a ground truth, so a lot of Y's. We know that we want this input to end up to be that output. Right now it's this output. So we can calculate the cost, how much is it wrong? And this is now quite a lot. What we want is this to be 0. Because if this is 0, this and that would be the same. And we can see if we change W a little bit, we can see that the cost change. So there are some values where the cost is so small that it's, you can say it's 0, close to 0. And that's the whole goal of this machine learning, because then we know W and B, what's the best W and B to fit the X to be Y. So if it's not completely clear, we have a lot of more examples coming up, and then you get a little bit more of a feeling of what's happening. Just to describe the cost a little bit, like Darien was telling, it's like telling how much the model is working with how good it is fitting the data, how good it is to find the good solution. How we do this right now, I'm subtracting the prediction with the ground truth, so you get the difference between what the model predicts and what the final result should be. I'm squaring it here to make it positive. So we want a positive number for the cost, because how higher it is, how more wrong the model is. And what we want is the cost to be 0. So squaring it means like it's always positive. And it also means that very big differences are even worse in cost. So if it's a small error, it isn't that much of a cost. But if it's a very big error, it really grows fast. And what we just do here, we take the average of all the losses, all the costs, all the errors, and this is our final cost, our final grade of our model. Now, to see this in math looks a little bit scary, maybe, this equation. But what it is exactly what we did here. So to break it apart a little bit, L is here. It's called the loss or cost. What we're doing here, and it has an input X, which is our regular input we train it on, and input Y, which is our ground truth where we want to be, and the W and B, which we want to learn. Here is the line equation again, W times X plus B. Here we subtract the Y pointing to the ground truth. So it's what happened here. That's this guy, subtracting the line of the ground truth. And then we square it, as you can see here, squaring it. And this guy here is just taking the average of all the i's, so all the samples we put in, and all the samples of the ground truth, we all add them together and divide them with the amount of samples, so we get the average of the cost. So this is exactly the same as that. Here we described it a little bit. Now, and the whole goal about machine learning is then to minimize this function, which means like to get the cost as low as possible, to get to 0. And how do we do this? There are 4 inputs, but we can only change 2, W and B, because the input and the ground truth are fixed. We cannot change the banana. We can only change the parameters to detect if it's a banana or not. So how do we do this? What is minimizing a function? We made a little, maybe you saw it on Facebook, a little tool to describe how it looks like if you visualize it. Think about this as a function, as like this math equation where the position of the ball is some kind of W and B, some kind of coordinate of the input. What we can do is then look around how the slope of the function goes and take a step and do it again. If we do it like that, eventually you get to the minimized, the lowest function of the lowest value of the function. And it doesn't matter where you do this, it always goes to there. So the idea is, if we have this equation, this function, and we know which direction it goes to, we can take a little step towards that direction and do it again. Check out, like, okay, is it better, and where does it go now? And then take another step and another step. This will get more clear in a bit later. We will get back to this again later. But yeah, the most important thing is we need to find the slope. Where does the function go to? And how to do this is using calculus. Not sure you're familiar with calculus. It's a bit annoying subject. We made a little tool to show what it is. It also maybe looks a little bit scary, this guy here. but this is the main function, the main equation of calculus, and how to find the slope of the function. So where does the function go? Does it go up or does it go down? And we can show this by changing an x here. And we have a dot here. Let's do this as well for now. Okay, so if you see this function fx plus h, fx is this guy, the green one. We just plotted it, and now we just fill in an x, minus 1.6 in this case, which is this point. Then we add something with h a little bit further, in this case 2 point something, and it's another point. Now we can take a line between it, and the whole idea about calculus is that h is becoming smaller and smaller, closer to 0. And what happens then if you do this, closer and closer to 0, you get a line that is tangent to the function, wherever you are. So in this case, you see it goes, here it's at 0, it doesn't go up or down. Here it goes up, and here it goes down. If we plot this, it would be this. So the gray line here and the dot describes like what the slope is. Here it's 0. Here it's positive because it goes up. Here it's negative, so it goes down. So the whole idea is knowing this number means that you know if it goes down or it goes up. And that's the whole key about calculus. It's a bit hand-wavy maybe. There's a lot of examples here how to derive such functions, how to find this slope. We're not going through it because it's quite boring. If you're really interested, you can read a little bit of those things. Here are some more complex examples. And we can explain a little bit later, maybe drinking a beer or something. But it's or vodka, even better. One thing I wanted to notice is the chain rule, which is it's also like a calculus rule, and I'm not going to really go into it because it's also a bit tricky. But what it means is that you can take a complex function, a very big one, and take it apart in parts. And this way, it gets way more easier to have a really big equation and find the slope. The slope, by the way, is called the derivative. So find the derivative of the function. Yeah. Yeah, so with this idea, we're now going back to our little line example. So we saw this earlier. The input, W, B, and the ground truth makes a line, creates a prediction, and calculates the cost. How much this is wrong. But now, what we can do, we can also find the slope. What we just saw with the calculus, we can see where this function heads to, this cost function. So if we go in, okay, yeah, you have to believe me on this. This is the derivative of this function, squared, yeah. So you get a derivative of only this part. So only this part of the function shows like, okay, where does it go to? And using this chain rule, we can, okay, yeah, first let me say like, this part is called forward propagation. So it means like calculating the whole function forward and calculating the cost. So knowing how much is wrong or right. Then calculating it backwards using this derivatives, using the calculus techniques. It's called backward propagation. Okay, and this is a little bit complex. It took me quite a while to really understand it, so I'm I hopefully get a little bit of an intuition today to dive into it, because I'm not 100% sure it's very easily to understand. Again, using calculus, we can find how much of the weight, how much of the W affects the final loss function, the final cost. So how much, if you change W a little bit, how much does it affect the end result? Same goes for B. And you can also find the derivative, find the slope, find how much does the output change if you change X, which is the banana in this case. So we cannot change X, so we don't need this here. But later on you'll see we can continue doing this. And using the chain rule, we get further and further and further. I explain it a little bit here with the math stuff. Also, if you're very interested, then yeah, please read it, but we're not going too deeply into it. So if we know the slope, if we know where the function goes to, we can take this little step. We can update W and B a little bit to end up closer to prediction what we want. It's called optimization. So simply, we have the derivative, where does the function go to? And we just, why is this? Yeah. So we add this with a learning rate. That's gone. Yeah. So I'm adding here constant really quickly. Learning rate. So this is a rate, how far we want to update this W and B to get closer to this answer. If you take a big step, you can maybe really jump over this minimum we are looking for, and then yeah, you're lost. So it should be small steps every time. Look again, like, are we closer and how much? So delete. Oops. So for example, 0.1 in this case, it just takes the derivative, the slope, and times 0.1 is a value we can update the weight, the W and B, and that's exactly what we do here. So we have a W and the B, how much we can take the step, how much we should change these values to get closer. And as you can see here, we're just updating the value of the weight. The guy here, this one and this one, using the updates. Now if we do this, yes, it's what we can do is make one base here. And call this sections. And then I think it should work. No. To alpha. So I kind of broke it by moving everything around. Okay, I'm going to change this really quick. No. Sections. Yeah. Up section. I will just do it like this, and here as well. Section. Oh, we can just do it like that. Hoppa. Okay. So if we press learn now, what we do is take a step, update this W and B, and do it again. Take another step, update, take another step, update. And if we do so, it still doesn't work. Here another one, sorry. So this one 5, and this one. Right. Okay, let's try again. If you press learn, this doesn't work anymore. Yeah. All right. So now if we press learn, yeah, there we go. The cost goes down and approaches 0. So we're getting closer and closer, and as you can see, the prediction lines up with the ground truth. So it finds the right W and the right B. We do it again, reset it. You see the W and B changing so that it fits this data. To make it a little bit more interesting, we copy this one because the other one is broken as well, I guess. Hopefully this one works. We will update a version that works and send to you all, so you don't have to update this yourself. Okay, so what we did here, exactly the same, but instead of one input, one X, we have 2. We use 2 inputs, X1 and X2, but ends up to be one result. And why I'm doing this? To make it more visible, because now we can use X1 and X2 as 2D coordinates. So we can say X1 is X and X2 is Y. And if we do this, we can plot it. So in this, hopefully this works. So those are all the X and 1s, X1s and X2s. Where X1 is the X coordinate, X2 is the Y coordinate. Then we can make dots where those positions are, and we color them according to the prediction. If it's below 0, it's green. If it's higher than 0, it's red. Now we want to find the line somewhere around here that divides the red one from the green one. Now, let's hope it works. Okay, resetting works. When I press reset, it just takes random values for the W's. So as you can see, it just does random stuff. And if I learn it, you can also change the things a bit here. And it keeps on learning it, unless we do that. So this is the whole idea about the basic idea about machine learning. And now we just have two inputs, X and Y. But imagine a lot of inputs, a lot of calculations ending up almost exactly the same. So, for example, banana doesn't have just X and Y, but has like all the pixels is like one input. So all the colors are one input, and the output can be either 1 or can be 20 or whatever you want. But it's all the same idea. So it's all finding that W and B to fit the data to get, okay, and maybe is a bit hard to follow, but I think in the next couple of models you will understand it more and more easily, because it is a bit of an abstract solution of an abstract problem here. But yeah, we'll see in a bit how it works out. I think it's not, we're quite fast, so a break is better to do later, I think. So what we're going to do now, or Darien is going to tell a little bit about the same thing, but on the GPU. Because this works perfectly on the CPU, but if you have a lot of data, it's going very slow, and we don't want that. So I give the mic to Darien.
Thank you, Menier. Okay, so yeah, like Tim explained you, we have now to consider what happens if we want to have more features. Features are these inputs that we're feeding to the model, so these x's. So in the last example, we saw that we provided two x's, and we plotted them as xy coordinates in this Cartesian space. Okay, so we're trying to build up to TDNeuron, which is capable of doing many features. But we need to start somewhere. So we're going to start in the same place as before. We're going to use only two features, also x, y coordinates. So I want to present you first what is the difference between what we're going to do now and what Tim just showed. So the difference is that before we saw something called linear regression, and now we're going to do something called logistic regression. So if you see here, I wrote what's the difference. Essentially, it has to do with the outcome and the variables that we're dealing with. Because in a linear regression, the outcome is continuous, meaning that we don't really have separate classes for the output. It's just one single set of values that we want to acquire. However, with logistic regression, this has classes. So we can classify between a type of data and another type of data. And why do we want to do this is because we have now a slightly different problem than before. Before we wanted to model this line that changes over time. Now, however, we want to distinguish between two different classes of points in space. So for you that if you read the material, the first example that is in the material in the tutorials is this. Okay, so as you see now, I have a table with coordinates, x, y, and classes. So let me show you how this looks like in space, because then it's very concrete what we're trying to do. So the way this looks like is like this. So ignore the cubes behind. Focus on the little balls. So this one is class 0, and this one class 1, because as you see, they are separated in two different realms in space. What we want to do is to train our network so that it can tell us, does this point belong to class 0 or 1? And if we do it at the moment, let's skip that. It's enough if you see the classes. This is clear, right? We want to predict between these two classes, and we want the machine to tell us which point belongs to which class. That is the problem we have. Okay? Is all clear about that? Awesome. So now what we're going to do is to do it in GPU, because we want to scale it up so that we can provide not only two coordinates, but many thousands of coordinates. All right. So as you all know, we can do this with conversions. So we're converting the data first to chops, then to tops, and we're encoding these XY coordinates in pixels, in RG, in the RG colors. So these are 2 channels, and we have also the classes encoded in a single channel, in the R channel of this other top. All right, so these will be our features, what we before were calling X, and this will be our ground truth. The classes are the ground truth, because we want to the computer to tell us to what class it belongs. So that's the ground truth. Now, Tim also explained before that we had a W and a B. Here is exactly the same thing, really exactly the same thing, and we're using tops. That's the only difference. So here we are also using 2 neurons, like in the last example, and they are encoded here in the RG channels. So this noise represents the W, the weights. And this constant represents the bias, the B. So before we saw that we had this, and we call them weights and biases. So that's what these things are. For now, ignore this thing here, why it's there. I will explain in a second. But let's now look at the network. So let me make a little quick jump before. In linear regression, we had this forward propagation, and we had this backward propagation. Here is exactly the same thing. We have a forward propagation, and we have a backward propagation. All right? However, now we're trying to make it modular, because we want to make a system that can do many problems, not only X and Y things. So we have made them into little nodes. Now let's go one by one exploring these nodes, what they're doing. So if we go to this first node, which is the linear layer node, so we see that we have the features, the X from before, we have the weights, and we have the bias. Exactly the same equation as before, Wx plus B. And what we're doing here is, since we're dealing now in a single operation with vectors, because they are encoding in RG, right? We're not having independent values, now we have a vector. We need to take the dot product between the weights and the inputs. And then we're adding our bias. So this is the equation that we saw before. It's the same equation, but now it's with vectors. And I think most of you know GLSL, so I think you know what the dot product does, right? Everybody knows? Yeah, perfect. Perfect. So that's what's going on here. It's very simple. As you see, that's it. So we're sampling the inputs and just doing the dot product, and then that gets the output. We're calling that output Z. Perfect. Now, since we have now this classification problem, we're going to add an extra layer that we didn't have before. And this is called the activation function. We need to use an activation function because we're now dealing with a different problem, which is to classify between 2 classes. So we need to devise a mathematical entity that would allow us to define which one of them belongs to which class. So now let's make a little step before we go into the code to explain you what the activation function does, okay? So now you can wipe everything out of your head, forget about equations, now just focus on the activation function. So let's go into this little helper tool that I made for you. You can open it. And here you see the 3 activation functions that we're going to deal with in the whole workshop. These are the sigmoid function, the tanh function, and the relu function. So let's begin with the sigmoid function. As you can see from this graph, the sigma function looks like an S in the range between 0 and 1. So you can see this is 0 and goes up to 1. So let's see what it does with a value. The sigmoid function let's say, compresses values between these 2 ranges, 0 and 1. Why is it useful for us? Because we have 2 classes, right? We have a class 0 and a class 1. So it's a perfect mathematical entity for us to use. So if we change the test value, we see that the further we go along the x-axis on the positive side, the sigmoid function compresses it so it reaches 1. So if we put here, for example, 4 or 5, you see that the value approaches 1. So it doesn't matter how big it is, it will always be approaching 1. On the other side, if we do the same, but on the negative part, it will make it approach 0. So as you see, it compresses any value that we fit between these two ranges, 0 and 1. Is this clear? Awesome. OK. Now, this is the basic intuition. That's all there is to the activation function, really. So let's see another one, the tan h. The tan h we will use in the next model we're going to show you, but just so you are aware of it, is the same, has a very similar form as the sigmoid function. However, this one goes between -1 and 1. But that's pretty much the same. So if you see, when I increase the value on x, the bigger it gets, it compresses it to be between -1 and 1. So it doesn't matter how big it is, will be 1, or how small it is, it will be -1. And finally, we have one extra activation function that we use in TDNeuron, which is ReLU. And the ReLU is the rectified linear unit. And what it does is it compresses the value between a 0 and whatever other value there is. So if you see, if we go below 0, it will always be 0. And if we go above 0, it will be whatever that value is. Yeah? That's all there is to activation functions. Any questions about it? Awesome. All right. Yeah. So let's go into the code of this. So if we see the activation node, we can check the code here. And it is extremely simple because I am just sampling the output. I'm sampling the output of this linear layer. And I am just taking that sigmoid function that we just saw, which is defined in this way here. So this is the sigmoid function definition. And I'm just taking the sigmoid of that value. That's all the activation function does in this network. Right? All right. Finally, like if you remember from what Tim said, we need to also use a cost function to tell us how far we are from the goal that we're trying to reach. And now this one is going to look quite scary, because it is scary. And it's called the cross entropy loss. OK, so this is how it looks like. This thing looks quite horrible, but I'm also going to show you, like we did with the activation functions, with a little helper tool, which is here. There's various loss functions, but I just wanted to show you now one, which is this one, the cross entropy. And if you see here, what it does is the further you go along x, you should see it in relation to this y-axis. So x, in this case, represents the probability. So the higher the probability for a value to be, the smaller the loss is. And the smaller the probability for a value to be, the higher the loss is. So as you see, it creates a huge loss if my probability for a value to be correct is very small. So if I go on the other hand and my probability is very big, it's like 1, then the loss is 0. That's why this is useful for us, because from the previous function, this sigmoid, we had a compressed value between 0 and 1. That's our probability. And this cost function is going to take that value and say, OK, where is it? Is it closer to 0 or closer to 1? And then it's going to compress that and check. If it's closer to 1, then the loss is small. If it's farther than 1, then the loss is huge. So it's a bad value. Right? That's what this cost function is doing. And now we can see again the code for it, which is this code. And let me explain you quickly what the symbols mean. Okay? So here the y is simply the ground truth. And A is simply the prediction we have. So Y is the ground truth, and A is the prediction. And we can tell because what we're grabbing here is the activated values from the weights, which came after the activation stage. That's this input here. And the ground truth, which is really is the class. So this one that we took from the beginning, which is which class does it belong to, right? That's what's going on in here. And then we perform this operation to get that curve that I just showed you. All right? Finally, because now we have a number of samples, we have 10 samples in this case. As you can see from here, we have 10 samples. What we need to do is to take the average of this loss so that we can compute properly the whole cost function. So we're just dividing by the amount of samples we have, which is now in this case will be 10. But we're doing it modular, so we're calculating it with these nice uniforms that TouchDesigner provides to get the resolutions. Okay, is it so far clear for everyone? Awesome. Okay, now this is the hard part, the backpropagation part. All right. So the backpropagation in this network, we tried to make it a bit more visual for you, because it's a real mindfuck, to be honest. So now what the backpropagation is doing is taking this part. So we're going forward like this, and we're going backward like this. And you can tell because of these nice arrows going back, right? All right, so what needs to happen here? We need to take, as you saw before, the derivatives of each stage to compute the overall gradient. It's called the gradient. So what is the gradient? So the gradient is just a collection of all the derivatives that there are available to us. Okay? In this case, we have a vector with 2 because we have 2 neurons, 2 weights. So let's see how to take the derivative of this horrendous cost function we just saw. So if we go inside, we see the code remains very simple because we're just sampling from before. However, to take the gradient, which is this collection of derivatives, we simply take the negative of the ground truth, which are the classes that we took from before. We divide that by the prediction, which is the output from this guy. And then we sum that by 1 minus the ground truth divided by 1 minus the prediction. That is how we can compute the derivative of this cost function. Mathematically, I'm honestly not able to explain you why this works in a deep way because I'm not a mathematician. So you feel free to check it online. But the intuition is that you need to have a pair of value and a gradient. And this is called the local gradient because if you remember from what Tim said, we're applying the chain rule. The chain rule, in simple words, is just the following. So the chain rule is, it simply means take the derivative of each independent stage and multiply it by the next one. And then what you end up with is the overall derivative of everything. That's the chain rule in a very hand-wavy way. Okay? Perfect. So then what do you think will be the next step? Someone can tell? No? The next step is to take the derivative of this guy, because we're now going backwards, remember? So we went first forward, took the derivative of this guy, that's here. Now we take the derivative of this guy, that's here. And if you see, they correspond 1 to 1, right? So let's see. The input for this one is going to be the output from the previous one, which is this one. This is the gradient. So this fits into the backpropagation activation, which is simply the derivative of this sigmoid function that we had before. And you kind of have to trust me on this one, but the derivative of the sigmoid function is this expression. Yeah? And what we're doing is taking the derivative of the gradient using the sigmoid, because the gradient is the previous step, and then we are just multiplying it by the local gradient, which is the value that we grabbed from before. So that gives us the new gradient, because we're flowing backwards, right? All right. Any questions at this point? No? Okay. So what's the next step? No one? Yes. Take the derivative of the linear. remember that you have to take the derivative of every single node that we have. So we take the derivative of this guy. The derivative, in this case, looks a little bit more complicated, but it's not. It looks because we have now two shaders suddenly. But we did it like this, so it is easier to explain. First, we take the derivative of the weights, because if you remember, whoops, if you remember, here we had our weights and biases and our features. That means that we have to take the derivatives of our weights and our biases. So if we check here, the weights derivatives get calculated in this way. It's simply the sum. If you check the code here, it's just simply the sum of the multiplication of those input features that we have times the gradient, so the previous calculation we made. And that's it. That's all there is to it. Bear in mind that our inputs are in the form 2, 1. So this is a vector still. It's not like we're dealing before. We were dealing with just single numbers. These are vectors. OK. And, and the bias, the derivative of the bias is simply the sum of all the previous step. So the gradient that we had. And that's all there is to it. Now we have this, yes? Yeah. So the derivatives of the bias is just the sum of all the values from the previous step. All right. So now we have them here. Now, if you remember from what Tim was saying, we need to perform the optimization. The optimization is updating the original weights and biases we had minus these new values we have, so that we can go, remember this graph, we can go closer to a minimum. So we have to subtract the original weights minus these guys. Weights and biases, sorry, minus those guys. And that's what this guy here is doing, this update. And if you see here, it's very, very, very simple. It's just grabbing the original weights and the derivatives. The derivatives get multiplied by a learning rate. This is how big is the step of this slope that is going to go to a minimum. And we are subtracting those two values and getting an updated set of weights. And we're doing exactly the same with the biases. Yeah, that's pretty straightforward. And now, I hope it works. Let's see. Let's see if it can learn something. OK, so we start with this thing here, because we have a set of values on the bottom part, set of values on the back, and this thing on the back is going to tell us by color to what class it belongs. 0 means 0, and black means 0, and 1 is white. So we're going to train it. We see that the cost goes down, down, down along the very small now, 0, and you see that it has colored correctly this set of values and this set of values. Now we can ask it. We can say, OK, what do you think this is? I say my prediction is 0, and it's indeed 0. So these are the data that we fed it, and this is what the computer is telling me it thinks it is. And let's see about this one. It says it's 1. So it has learned it. So if we do that, but let's use now a smaller learning rate. So let's use, for example, 0.01. And I tell it now to not train. Now we see that the space, he doesn't know, because this is still whitish. It's not sure. So if we ask it now, he thinks now that the first one is 1. However, we clearly see that it's 0, so it's wrong. So let's let it train a little bit. Maybe the training rate is a bit slow, but let's see how it does it. So now it's approaching lower, lower, lower. Now already thinks it's 0, this one, for this one also, because you see my cost is decreasing. So you see that it's approaching the right values, and this will get colored progressively to be of the right class. So yeah, this will take a little while, but is it clear so far? Because, yeah. Yes, in a moment, we're going to see why we need to make smaller learning rates sometimes, because if you make steps that are too big, you might miss your target. All right, so slowly you see it's darkening this part. Okay, so I hope this is very, very clear. Now, I said before that we're going to try to scale the system up so it can support not only X, Y, but it can support a huge amount of input features. Because at the end, we want to classify other stuff, not just coordinate systems. So let's now talk a little bit. Oh, yeah. A little break. Do you want a little break, maybe? Maybe we can take 5 minutes just to refresh, and then we continue. Yeah. Okay. Okay. Yes. So if it's going a bit too fast, don't hesitate to tell me. Okay. So now we want to jump back a little bit to the visualizer that we saw before, that Tim showed, because there is a problem when we are trying to do machine learning, a very, very crucial problem. And this is related to what Vincent was asking about the learning rate as well, but it's more about how to find these places that are optimum. So yeah, so before we had this thing, we had this space and the local optima, so the best solution where the cost is 0, is represented by this green area. But usually when we're trying to do these machine learning processes, we never have these kind of situations because we have a very complicated landscape. And you can visualize it like Tim said, like if you're in a mountain and then you're like blind and just trying to find where to go, blind completely. And you can tell by the slope of the terrain. So what if we have a terrain that is like warped, so something like this? Then if you see, we start to have many different small pools of values that seem to be the local optima. And what happens here is that our learning gets confused. So if we do this, now it stopped there, but it's not really the true place that where it should stop. So if I throw it somewhere else, it gets stuck there, here, there, here, there. So it's doing really terrible now. So we need to devise some strategy to deal with this problem. And the strategy is to apply a set of further optimizations to the algorithm. So this is not something we're going to go into much detail, but it's something that is built into the TDNeuron package that we're giving you at the end of the workshop. And it's a different type of optimization for the algorithm. How do you call it? What's the proper word for this? Yeah, is it optimization technique? Yeah, okay. So we will call this the optimization technique. So the solution is to add small momentum to the motion, because in this case, we're gaining velocity as we approach some place, and if the place ends up being quite close to the optimal median, but not quite, it will do this, like it will get some friction, but it will keep going and find the proper place. So let's see what it does now with this new optimization. Aha. Now it's, because it got this velocity and got a little friction here, but it could go further because it had some momentum. So that is one way which you can solve this problem, which is called local minima. And it's a very fancy way of saying multiple places that seem to be the right answer. Okay? So we have this thing. Feel free to play with this. You can also change the frequency of the noise to see how it performs with different structures. And also, I suggest you to play with learning rates to see how this affects the process. So if we see a smaller learning rate, and we do this, we see that even though we have momentum, it got trapped there, because my learning rate is just too small. So you need to tweak it to find the right learning rate so that it can escape that spot. So let's try something else. Okay, now it escaped it. It's really fast. But yeah, this is the most important parameter, the learning rate. And we call these parameters, we call them hyperparameters. All right? So feel free to play with this little tool later after the workshop to understand better what's going on. Okay. Now,
This running rate is like its initial speed, or
it's like the, yeah,
in this metaphor.
the steps. Yeah.
It's like how far you take a step, check again where this function goes. So it's like you update it a little bit, and look again. If you look back and do it per step instead of automatically. It would be like this. Every time you take a little step.
And on the map it is the white lines, right? They mark this that or it's
No. It's the white lines just describe.
I described it in the other video.
Yeah. So if you see, like, if we take a smaller one, and we take the same kind of step, so now the step is very small. So we do these very small updates. So the further we go with problems, you will see, yeah. Maybe did we do some include? I don't remember. Let me see. Yeah. Okay. Maybe we use something that is not supported, but yeah. Okay. All right. The further we go with machine learning, we will start to see these kind of little problems, and for every problem there's a little trick to solve. But also I want to tell that for us it was super interesting to get into this research because it's an active topic. So there's no one good solution yet. Even the genius mathematicians that come up with this stuff, no one is really certain why some things work and what is better in some cases. So it's very fertile field for us to research. And some, yeah? It's like this. There's no method. I mean, yeah.
It really depends on the data you're giving it. Because some data is like very hilly, but some data is very smooth. So then, you have to tweak a little bit and find the right learning rate to get.
Yeah, you have to spend a little time playing with the model to see what's the best. Yeah, but it really depends on the problem, and also depends on the little additional optimization techniques that you use, because there's many. We just show now one, but there's other. All right, so like I said before, the goal of moving into the shader world was to expand it, right? We want to have many features, not just two. So now before we do that, we need to get acquainted with the concept of matrix multiplication. How many of you know what this is? Matrix multiplication? Multiplication? Yeah? Okay. So I will explain it because the equations, they're changing a little bit, not too much. Before we saw that the equations were like this, wx plus b. Oh, sorry, plus b. Shift. Oh, yeah, okay. Okay, wx plus b. And we saw that there are small letters. That's because they are single values. However, now we're moving into a territory where there's not single values, but many. Therefore, they are now capitals. And in math notation, the capital means it's a matrix. So what is a matrix? We all know and love these guys, right? This is a matrix, pretty much. But we created a little tool to explain you what this is, what the matrix multiplication is. So the tool looks like this. I'm going to feed it some random values. And as you see, this matrix here, the matrix A, is a collection of rows and columns. So the row is this, and the column is this. Now, we see that this matrix has a dimension of 4 by 3 because it has 4 rows and 3 columns. The rows, in this case, determine this part, right? We see the matrix B, on the other hand, has a dimension of 3 by 4. because we have 3 rows and 4 columns. And the resulting C matrix from the matrix multiplication between A and B has a dimension of 4 by 4. But what the hell is going on? Why? So we made it so that you can understand how this happens. If you click on one of these places, it will show you, it should show you, but it doesn't. God damn it. It does. Does it do it for you? Does it color it red for everyone? Okay. So I will not waste time trying to debug it, but I will just explain it. So if it does it for you, you will see that, oh, sorry. Here. Yeah, you will see that if you press on any cell, it will tell you what row and what column of each matrix is involved in the process. So what this is, for example, this one will be the result of this by this. So what is going on is just the dot product of that row against that column. So what is the dot product? Is just multiplying each one of these elements and adding them. And then you end up with this result. So if you really want to understand it, just look at your example that works, but not here. And you just click on it and see where does it come from. But the important part to remember is actually the dimensions. So look very carefully what's going on here, because I have colored it now like this. The red are the final dimensions, and the green must match. If you don't have matching matrices, the operation is not possible. So if you have here, for example, a 2 by 4 matrix, this is wrong. So if you try this in your example, it should give you an X here, I think. So try to change that to a 2, and it will show you an X, meaning that you cannot do that operation because these 2 dimensions do not match. So the condition is that this green part should match, and the outer part will be the resulting dimensions. So let's revise this very quickly. So if I do a 1, let's see, no, 2, 3 by 3 and a 3 by 4, then here the resulting dimensions will be a 3 by 4. Don't look at this because it doesn't work for some reason. But in yours, it should work. It should tell you that it's a 3 by 4 matrix. Yeah? Is it clear for everyone why? Everyone? No questions? We're good? Be sure to understand it because this is the most important concept from now on. Oh, okay. All right. Sorry for the bugs. We don't know. I mean, we changed something. I don't know. All right. Now, using this concept of matrix multiplication, we can now expand to more than just 2 features, because now suddenly, using these amazing dot products between the rows and columns, we can have many, many, many features. So let's check how that looks like in a concrete example. Yeah, where is that one? I think it's this one. Lift is 6. Shit. It works there? What the hell? Yeah, okay. I'm going to switch because there's an error that will break everything in the next example. Oh yeah, you get it. Okay. Yes, okay. So let's inspect this section 010. Like before, I'm going to dive you into the network first. Now that you know the principle, it's easier to get it, I hope. So now, I'm going to fit instead of 2 features. I see everyone's playing with the, with the visualizer, but pay attention to this first, please. All right, so first we have these 3 features, x, y, z. So we have an extra dimension. We had 2 before. Now we have 3. And we have now more classes. We have in total 5 classes. Before we only had 2 classes, but now we have 5. Oh, 6 actually. 6 classes. Okay. How does the data look like? Just to give you an idea, a concrete idea, the data looks like this. So this is what we're trying to classify. We're going to try to tell the computer to make the computer learn to which class does each of these points belong to. Okay? So this is what you should have in mind now. All right, let's check what's going on here. You can ignore this one for now, but let's look at this part. This x is the features we have. In this case, we have 3 now. So this is going to be a 500 by 3 matrix. Because 3 is the amount of features we have, 500 is the amount of samples we have. So now we're dealing with matrices. So it's not anymore a vector, it's a matrix. In this case, the ground truth is 6 or 500 by 6. So because we have 6 classes and 500 examples. And if you see, the 500 corresponds in both cases because, of course, they are the same size since we have those amount of samples. Now, inside the network part, I have created now this in a more compact way because this is pretty close to the architecture in TDNeuron. So if you observe this, then you can understand TDNeuron better, I think. Now we have this library of different layers. So if you see, we have the linear forward layer, where we do the weights and biases calculation. Then we have the activation forward layer. Then we have something new, which we skip for a little bit now. And then we have the cost and the optimization. We also have now 2 new layers to generate weights and biases. OK, so let's inspect this very briefly. What is this? The generated weights is just a noise stop that is going to give me the values of 3 different neurons, in this case, because we have 3 different inputs, right? X, Y, Z. So the bias is going to give me also 3 different values because we have 3 inputs. OK. Let's inspect now the network. So if we go into the network, it's very similar to the network we had before, but it's a little bit bigger. Why is it a little bit bigger? It's because we need an extra layer to be able to compute this space. The space is much more complex now. It has depth, height, width, so we cannot describe it just with one line anymore. We need to create more planes to be able to describe this space. Therefore, we need to create a mechanism for the machine to do that. And the way to do it is add more neurons or add more layers in between. So, OK, what does it mean to add more layers in between? We will call these hidden layers. These are a set of operations that are exactly the same thing that we're doing before, the linear activation and the activation function. Sorry, the linear layer and the activation function. And we just copy them. And we stack them together. That's what these hidden layers are. And we do this because we want the space, the search space, we want it to be more complex. We want it to be able to determine in these 3 dimensions what the results are. So that's why we're using more. In this case, we're just using 1 extra hidden layer. So if you see, we have the linear layer. It's the same from before. Nothing has changed, exactly the same. Then we have the activation. Then we have another linear. And then we have this new thing that we didn't see yet, the soft max. But just to prove you that it's the same, let's dive in quickly into the linear. And we see that the code is the same as we had before. However, before we were doing the dot product of a vector, now we are doing matrix multiplication. So if you understood the matrix multiplication concept from the previous note, then this should be more or less clear, because that's what's going on here. So we are taking the samples from an input and the weights. We are multiplying each of those that correspond to each row and column in the input. So you can see here, this is pointing to the right row of that input, and this is pointing to the right column of that other input. We're scanning through it, and then multiplying them and adding them to determine the value of a single cell. Yeah? Is it, if it's not so clear, you can go back to the matrix multiplication node and just see how it's really done. How does that work? Okay. So that will compute this value, and that will give me a new matrix that it should be the size of these rows by these columns because of matrix multiplication. And we can see that indeed, that is, oh no, sorry. Oh yeah, sorry, it's fine. So we have 500 by 12 because of matrix multiplication. Yeah, one thing that is worth also to conceptualize, maybe, for me it was a bit messed up when I was trying to do it with the shader, is because with textures, the rows are actually the second, not the first value. Because resolution X, it's actually the columns, and resolution Y is the rows. And usually when we deal with textures, we say width and height instead of height and width. So that might be a bit confusing, right? Okay, so that's all there is to it. Now, there is a small change in the activation function that we're using, not really in terms of the structure, but just the activation we're using itself. Remember I showed you that we had many different activation functions? We're using now this tanh function. And the tanh, it was this S that goes between -1 and 1. Why are we using this now? It's because we need this intermediate hidden layer to not cancel all values between 0 and 1. We don't want to classify anymore between 0 or 1 class. We want it to just approach some other value that is going to be taken by a different cost function than before, which is the softmax that we saw. Okay, let me try to explain that in a better way. So we have this here, we have another layer here, and then we have this softmax. Before we had here a sigmoid, if you remember, in the previous one. So let me show you. We had in the previous network, here. We had this structure. So linear, sigmoid, cost. Because the sigmoid was compressing values between 0 and 1, and the cost was checking how far that is from our known ground truth. However, in this case, we don't have that sigmoid there, but we have this softmax. And this is because we now don't have only 2 classes, we have 6 classes. So we want the computer to be able to recognize between 6 different things. Therefore, we need a different strategy to determine the probabilities for each class to occur. So let's check how that looks like. Yeah, this is scary. And I don't have, I didn't make a clear visual example of this. But let me just tell you that what it does is just trying to give you an estimation for probabilities for all those 6 classes instead of just 2 classes. And it's a function like the thing we saw before, but it's a slightly different function. I will try to put this online maybe so you can see it. But OK, now you have to trust me a little bit. And after that, we have the same. We have the costs forward, and then we see we have also a backward propagation that goes all the way back. So the same structure, forward, backward. So can somebody tell me what should happen here? Someone? We need to take the derivative of the cost, right? So that is derivative of this guy here. And in here, the derivative of the softmax. And in here, the derivative of this linear, and so on. Same structure as before, it's just one extra layer that we have, or hidden layer. And if you see now, I have also the optimization parts, which are updating the values that are coming from here. And these values are being fed to the original weights and biases that we had before so that they can decrease and they can reach a local minimum, an optimum minimum, yeah. Yes, the code for this is not harder than before. It's just a little bit, maybe 2 lines extra because we have a different function. So let's check it here. So the extra thing is that now we're doing all the time matrix multiplications. But it's just that, it's just matrix multiplication, nothing really crazy. You can see here, this is the formula for it. There is a component here, T. This means transpose. It's because of the rule that we saw that dimensions of matrices, they must correspond in the inner part. So sometimes we need to flip them so that they match, and then we can multiply them. That's what this T is there for. And if you see here, this is slightly different than in the previous code. Here we are transposing the matrix, so we are reading it in a different way. Is this more or less clear? It's a little bit too fast maybe, but it's just so you are aware that we're doing this matrix multiplication all the time, and that the dimensions of the matrices are important, and that they must match. So that's why we're doing this little transposition here. But besides that, the code remains pretty much the same. Okay? All right, so now, as before, we have a cost. The cost is going to tell us how well we're doing. And now we can go into the visualization and see what is going on. Let me see. First, yeah. Let's see. These are the spaces we have. This is the data we start with. Now, what I'm going to do is I'm going to try to make a space map and make the machine learn this space map and tell me which spaces are what class. So we're going to create this distribution map. So we start with this distribution map, which is a 3-dimensional block. And if we train this, then it's going to be able to detect the spaces where the classes should lie. So let me see now. If I decrease the size of it, you will see that it has classified where more or less the spaces are, but it's not really doing it, and it's not really learning. Why? Oh, maybe learning rate, yeah. Yeah, so just the learning rate is 0, so of course cannot learn. So let's make it a little bit, maybe 0, 1. And now it's learning. As you see, it's moving something. So let's reset this, see it learning. Learning rate is very slow. Maybe let's do it faster. Just like this.
You have use rate. It could be -1 to the -10 or 1 to the +10.
Yeah, I mean, you kind of have to see how the cost is reacting. So if we see now our cost, we see that it's moving down, which is good. But it's going so slowly. So we can say, okay, do it a little bit faster. Maybe 10 times faster. Still doing well, but now it's much faster. So I like this better. So let's say what happens if I do it with 2. Oh, shit. Something happened here. You see, it spiked, but still reached 0. So there's some values that are better than others. I think 0.1 is a good value. And now we can go back and see how it learns. So let's go here. and reset it. When we start, you see how it's learning now? It's dividing the space and correctly predicts where these points lay. Because now the boundary for this space is red, perfect. Now this yellow space also is correctly classified, blue space as well. It's greenish space too, and the green here too, and black here too. So it has successfully computed every position. Now let me show you with a slightly more fun example. So distribution map, I also made this particle system. It's going to learn the position of the attractors over time. So if we do reset, it starts like this, doesn't know where to go, and suddenly it learns the position of the attractors. And we can see it also without moving. So if I hold it here, we see how it learns the positions. And when I release, it's just going to go to the right attractor because it already learned it. Yeah? So we see that there's a clear relationship between how the cost is decreasing and how our model is performing. And then you can do this kind of interesting applications of the algorithm. I mean, we try to create something playful, and these are very simple examples. But later on, you will see the true power of doing this kind of stuff, because you don't really need to program it, as we said before, linearly. You don't need to know the first rules. It learns by itself. You just create the canvas for it, and it just paints the stuff by itself. Any questions about this? I mean, all of you have the package, so all of you can check how everything was done. And all of that is in here. Here, in the visualization part. Feel free to just dive in and see what's going on and why it works the way it works. But the most important part is just what we showed before, this network here. Because all I'm doing is just getting the right classes, and based on that, I can do these visualizations. Okay? There's one remaining thing I didn't explain to you, which is this guy here, this data preprocess node. What is that doing there? Why do we need to do this? It's because some data has ranges that are huge. Like, well, this is not so huge, but still pretty big, minus 10 and 10. What typically we want to do to optimize the way the algorithm learns is to how do you say that? Constrain. Thank you. Constrain the space of the values that it's going to search to be in a sensible range. Since we're using now the tanh function, which you saw was between -1 and 1, it will be useful for us that also our data goes in that range. So what I'm doing now here is indeed normalizing that, so making it to be in the range from -1 and 1. Let's go into this guy. See that? It's not the most elegant way to do it, but it works. And we end up with this range. But we also need to zero center it because we want to move it to be in the negative and positive range. And that's what I'm doing here. So we end up with this minus 0.5 to 0.5 range. We have normalized it and moved it to be in a bipolar range so that the tanh function can make the most out of this data. That's pretty much what's going on. And that's why I did this data preprocess. You can also try to see what happens if you don't do it. Maybe it learns slower, maybe it doesn't learn. I think in this model maybe it still learns, but yeah, feel free to play with it. And I think that's more or less it for the build-up to TDNeuron. Maybe you have some questions that we can answer at this point before we dive into that.
So with rearranging, what if it weren't just X, Y, Z where they're kind of interrelated, but you had some kind of other dimension that was...
That's a very good question. That's a very good one. So you also have to clean your data, because indeed there's some cases where the data that you have is not meaningful for the output you want to achieve. So in that case, you can just discard that point, and it will. That's pretty much what we did with this model that Tim showed. He got rid of all the, what was it? All the orientation and.
The translation of where it was, so it only checked from the tip of the fingers and then relatively to the hand. So it doesn't matter where it is. It only learns this correlation and not like
yeah. So there are these three basic preprocessed things. Indeed, clean your data, normalize it, and zero center it. Yeah? Anything else? Other questions, doubts before we dive into TDNeuron, which is the fun part? I hope. Great. All right. So maybe you can. Oh yeah, the particles is just like to excite you a little bit, because otherwise it's very boring with just dots. And what is happening in the particles is just here. So I was just grabbing this space. Then I'm gonna take all the model. This is the learned model. So if you see, I explained before that once you learn something, you don't need to train it again. So I'm just taking a copy of the forward pass. It animates according to it learns the attractors, but the animation is for free because the attractors pull the particles. So if you see the code here, it's a little bit beside the point, but okay. So if you see this, what I'm doing is just have the particle, and then I'm grabbing just here the positions and the classes. The classes are the known truths. And this is what's changing, the class. So at the beginning, all the classes are 0. So all of them go to 1 point. But progressively it learns, and they start to go to the right place. That's what's going on there. OK. So now we're going to TDNeuron.
All right. The only problem is it uses compute shaders, so apples won't work, I think. It's not gonna do much. So it's in the TDNeuron folder. Opening it up. So to describe quickly a little bit about the structure of the system, we have a couple of components. Mostly this is the important one. There is where the model exists. If we, for example, go in, we see here a little bit the same like Darien also told. But the backward and forward propagation is in one component now. So here you have a linear layer. If you look into this, you have a forward part and a backward part. So here the derivative is being calculated, and this is just the forward line thingy we were talking about. And here are the weights of this layer. So we made it more modular, and that we can stack this up, have different kind of layers on top of each other. Starting with a linear, then an activation. This time it's a ReLU. And continue like that. This is like 3 layers, ending with a softmax and have a cost. Anyways, this guy, we don't have to set it up. We're using here in session. There are some dots. It's still, by the way, very beta. So it could be like that there are some like little bugs and stuff, but hopefully not. What we do here is like make a sort of data structure of how the model looks like. So we can like fill in those values, create those tables to create the model. There are a lot of settings and stuff. We won't go through them all. If you're very interested, we can talk about it later. But it's getting very complex. What this is, let's first show what kind of model this is. It's called, what it does is, there are some data sets. Let me see here. There's a famous data set called MNIST, which are a lot of handwritten digits by humans, and they classified it like, okay, this is a 7, this is a 3. So we have all the inputs, and we have the ground truth. So what what kind of character it is. And now we can train a model that can recognize that this is a 2, this is a 9, this, and stuff like this. We have 60,000 of them, 60,000 guys separated in 6 files. As you can see here, a lot of them. And we have the ground truth. So here we have the same idea what Darien described, like one top describing all the ground truths, and every pixel is which number it is. So this guy is 10 height. So this one is this one is the second pixel. So that means it's a 1. This is a 0, 1, 2, 3, 4, 5, 6, 7, 8. So now what we want to do is input a little image and finally get a result like this, so we know if it's a number or which number it is. So let's just do this in the info. If we look here, we see the cost. So we move the cost here. We're trailing it so we can see a nice line going to 0. And so let's keep this open. And in the control, we can control the model by learning it and stuff like this. So let's do this. First reset it, the weights reset it. I'm going to open this as well, so it's maybe a bit more clear. So in the linear layers, we have weights, these guys. And if we inspect it, as you can see, okay, then the top, all the tops are mono level, so we got rid of the G, B, and A, so only red channels. It's easier to understand and work with. So those are the weights of the first layer, and as you can see here in the red channel, it's a very small number and completely random. So we start with random W's, and those guys will be updated while training. So if we do this here, and we start training, as you can see here, the values are changing. Okay, there are some more colors going on, but that's what we just saw about the momentum. It also remembers like the velocity of the change of the weight. So that's the blue colors. Doesn't seem to work very well. The cost is huge. So what's going on here? Model. We can change the per linear layer. We can change all the hyperparameters, such as the learning rate, stuff like that. So let's change this. What we can do, that's a better thing. We also have an I/O, an input-output, where we can, this is a little bit very better, but we can load and save models. And we did already some pre-trained models, like this MNIST, this number. If we load it, as you can see here, the cost is way smaller now because we loaded now the pre-trained model. And if we look at weights, for example, you see it's like filled in. It's not small anymore. They got calculated. So in the prediction, if we open this guy, and here's the ground truth. As you can see, almost, that versus the prediction. Okay, it's not very visible, but you can see it's Um, it's the same. And so I made a little helper to make it more visible in the input model. This guy. So this guy just reads. Oh yeah, maybe that's easier to to explain. We cannot just put in pictures like that, you know. We had like this matrix with a lot of samples this way, and just features on that way on the rows. So what we have to do is convert this little picture into a row of pixels, a row of features, so we can stack them up. Every character would be like one sample, one column in the image. So what we do here in this little shader is doing this. So every column here is a row of pixels, and those are the same as the 2D picture, just like stacked downwards. And this guy, a little helper shader, converts it back. So you can just select one and you see what it was. Let's see. We can try to do it again by, if we reset it now, yeah. So here you can see how fast it also learns. So within like 10 seconds, it's already almost at 0. And that's because of everything is on shaders, so it goes quite fast. And then it crashed. So there you go already. Weird stuff is happening. And when the data is the shape of this loss landscape, what we showed in this gradient descent little app, can be really hilly or something like that. And especially with momentum, when you have a feedback, you can like totally get into another area where it's suddenly some kind of local optimum, where we are totally away from 0. And this is also what happens, for example, if the learning rate is too high. It can jump out and never get back. If we reset it again, touch. This is a bit annoying still. We didn't make a very good user interface yet. To change the learning rate, we have to change them all here. I can show you what happens when I do a big learning rate, and then start training it. Let's open this. If I now reset it and now start training it, it's gone. It's way too big, suddenly it jumps out and it can never come back. So making the learning rate, okay, still too big, jumps out, so even smaller. Yeah, this looks also not the best. So as you can see, it's quite trial and error to see what happens. It depends on it depends on the data you feed in. Yes. So one image here is 28 by 28 pixels. And if you stack them up, 28, 28, 28, 28, you get, I cannot count, 784 pixels. So it's just like all those rows or columns are like stacked. And those are the yes, yeah, yeah. So instead of what we did first with 2 or 3, it's now 784 dimensions. And it learns from the pixels, so it just sees pixels and knows then this is a 7 or this is an 8 or anything like that.
How does the resolution, like, as soon as it's recognizable, then it's because I guess like a higher resolution, like more features will take longer to train.
Yeah. Yeah, if it's you can, but yeah, you will lose data because the resolution will be smaller, and it's already with this one. This data set is not very sharp. There are numbers that looks like a 7. For us, it would be a 7, but it's a 1, you know, and that just depends on a few pixels. And this is still doable, but you have also with real pictures. Yeah, then if it's 32 by 32, yeah, you miss a lot of data, and the computer cannot figure it out as well, you know. But better than humans can. So that's maybe interesting to show autoencoder.
Maybe show also the working one. So if you did it actually does.
Oh, the drawer, yes, that's a good one.
Can you explain which part you need a compute shader?
Yeah, it can be written in normal with the feedback and stuff, but we're using it for the weights here. Which is this? Even a loop detector. This one, this compute shader. And why we do this is because we update it every time. And you can also make this with a feedback, with a normal GSL top. And I think we're going to do this, so it's also possible to make it work on an Apple, you know.
Yeah, I was just wondering if you were using a specific compute feature.
No, yeah, not for this, but maybe for the moment when you trained a model, it will be very nice to have the whole model in one shader, and then it's quite nice to have a compute shader, not, yeah, exactly, yeah. But yeah, for the training now, it's not really needed, so yeah.
Works for this data set. How does the known truth about this data set work?
The known truth.
Yeah.
Oh yeah.
Is there like a key somewhere that tells you it's like this is there one of these images when you run that you know what it is already?
Yeah.
Describe that to us.
So yeah, the train. Let me see. So the question is, if how do we know what the ground truth is of those images?
We need like data sets like that. Where do they provide like?
Yeah, it's a public data set. You can just download it, and it has 60,000 of those images with the corresponding digit. So you know this is a 1, this is a 6, and you can see this. I'm reading that in the input model. Let's full screen this guy. Mean test beds. Here, I think, no. Let me set. Job 2, oh here. So this guy, file in here. So this just 60,000 samples and 0 to 10. Yeah, I'm reading this from another file. But yeah, the first sample is the first image as well. So
So that's everybody in that whole set.
yeah. So there, as you can see, 60,000. And those are 2000 by 2000, so 10,000 per image. And there are 6 images. So there are the 6 guys. Let me see where the test thing is. So I made a little component. Just let's put it here. This is a trained model of the same thing. And now we can just draw here. And it finds like what kind of number it is. Or at least almost. Not super good because this data, as you can see here, already misclassified. Because this looks completely different than all the input data we gave it. It's not the same structure of pixels and stuff, so it's already getting confused. Similar with the leap motion. I was showing it, but
If I do it, it will not work.
no, it
It's 29 per year.
yes. Ah.
So this is kind of subject to the same like banana rotation kind of limit?
Yeah, in a sense, yes.
That's why it's very important.
Tell you, does it have a confidence level? Does the system tell you that it's not sure?
Yeah, in the sense I put it here, but it's also
Numerically somewhere it tells you.
yeah, it can say, yeah, but not completely. He can be completely sure that it's a 5, but it's not a 5, you know. So
But it doesn't tell you.
now, like this, okay, now it's a very low confidence. I show here the confidence level.
That's the confidence level.
Yeah,
Excellent.
but now it's high confidence. Yeah. Maybe another on a very, I really like it. It's called an autoencoder, and what it is, it's almost the same. What we do now is like, okay, we have a lot of input, and it goes down to one output, like being the digit, which one digit it is. But what we also can do is let it grow to not so much data, and then grow back to the 784 outputs and reconstruct the image. And instead of penalize the model by check it if it's a 1 or a 2, we just say like if the pixel is not the same as the input, that's the penalty, and do it all over again. It makes more sense if I show you. For example, yeah, this one. Sometimes I get this. I don't know why. Reloading it works. I think a TouchDesigner issue. Anyway, the model now looks like this, way bigger. I better learn the other. This one is nice. So let's show this first. This describes the model. And this is an autoencoder. What we do, we have a lot of linear layers, some ReLU activation, so flat and then like this. Then at 10/8, a different one, back to a few more, and ending up with a cost. And here we can see the amount of neurons we use for the weights. So the first one is 128, then 64, then 2. So normally to classify if this is a 1 or a 2 or something, we stop here and say like, okay, how much is it right? You know, we have only 2 outputs. But instead of doing that, we grow it again. So from there we go to 64, 128, and ending up with 784. And then what we do is calculating the cost between this output and the original input. So we don't even need labels. We don't even need to know if it's a 2 or a 3. We just give it an image and let it learn from there. And if we do so, this is the whole model. It's already learning. Still on. So it seems like it already learned the whole thing. Gonna use this little helper to convert it back so we have a more idea about what it predicted. So it doesn't really look like something yet. Some are. So what it did now is we gave it a 1, 0, a picture of a 0. It squashes it into two variables, two values, and then try to reconstruct it from that value. And then you create like, it's more like a compression of the image. And the funny part is, that's here. If we take a null here, for example, there's only two rows, so two values here, and that one goes into here. But what we also can do is maybe let's do it with a chop constant. X1 and X0 and X2, convert that chop to top. So now we have just one sample, and we put this one in the guy instead of the 1500. Then the output would also be 1, because we only have one sample sending here. And this output looks now like this, which is weird. Doesn't look like anything. Wow. But if we change this now, so it made a complete space of all the numbers, compressed in two numbers. It can recreate all the images, or almost, inside this. It's called latent space.
So you just have this kind of like two-dimensional coordinates of kind of zero-ish.
Yeah. Wait, maybe I have a... This guy, I guess. Hey, what's up? Oh, there. I think this model is a bit better. So it merges everywhere. Somewhere in space, there are those crazy numbers. Yeah. Yeah, well, I made something that display latent space. I think it's this one, huh? This is the 2D one. I thought I also had a... here, for example, here it blends between all the numbers. Same idea, but it's just one slider. But what I'm looking for, the first one was 1, just putting it back to 1. This one is 2, where I just put noise on the coordinates, so it jumps around. But I guess then we have to do it with this one. What this is, it shows, let's put this one here back. It shows by color, using the ground truth, which character is which digit. I give it colors, and if we increase the size a bit, let's say 10,000. Well, it's not very visible here, but what it does, it really clusters all the numbers together. Even though we didn't train it on what is a 1 and what is a 2, it really finds, okay, this part is a certain digit and this is a different one, and this one, and stuff like that. Maybe this one is easier to see. Here I did it, that one is, I think it's here. No, 10,000. Sorry?
Instance all the numbers to where they go?
Yeah, I did, but I cannot find them right now. I will look them up in a bit. And why is it not? Okay, it should be 3D. Doesn't work right now. Sorry about that. That's okay, yeah. Maybe some other nice models to show.
The banana one.
Yeah, the banana autoencoder. We also did the same thing with bananas. We need to add this one. Bananas. Is that the one, right? Yeah, I think so. So we have here 181 bananas, images of bananas, 3072 features, which means it's 32 by 32, but 3 channels because we have now colors. So it's 3072. This is an example of a banana of 32 by 32. Here you have them all, or at least some of them. And now what we do is put, okay, this can go. What should it have again? Sorry?
Can you check the fetch? I think it's third pixels fetch. I don't know.
So why don't I? Ah, the mean. So what I'm doing now is trying to train the same autoencoder what I did just with the numbers, but now on bananas. And it's just the right mean. Slowly all the images are changing into what's bananas. But maybe let's not wait for that. It's the one. It's a bit buggy now. Now maybe you can show something and I will check it out here and fix it, because later on it's there's no use.
Okay, well, Tim tries to find that one. Maybe I can show you. Let me see. Yeah, I mean, as you see, there's a lot of things that do not work because we're still working on them. And part of the idea of giving the workshop also was to create some interest for you guys to contribute if you feel like it and to research about it. We're going to release all the code in a GitHub, a functional code, very soon. It will be a basic iteration of TDNeuron, so it will be a beta version, but it will have all the things that you have seen so far. So you could train these classifiers, and you could train, possibly we're going to include the autoencoders as well. And we're developing now other kind of networks too, so convolutional neural networks, and we want to reach also generative adversarial networks, and all within the TDNeuron. So maybe I want to show you a little bit of the work in progress stuff, so you are aware that where this is going, and also where you could contribute, because we really need more hands on it. It has been just the two of us for like a year and a half or something, doing all this stuff, and yeah, it has been a bit like steep, you know. The slope was very high. So that's why we called it.
I'm curious, how does TDNeuron compare to existing tools?
Yeah.
You were compelled to do it to understand how things were working.
Yeah, I mean, there's two sides to that. There's the, of course, in practice, when you want to do a big project with a lot of data, you cannot compare the performance of TDNeuron with a model like TensorFlow or Keras or something like that, because those are, of course, engineers work on them for many years and they are optimized. So performance-wise, that was not our intent so much as to provide the community with something that they could use to understand it in a language they feel the most comfortable with this within TouchDesigner. So I think the advantage of doing it in this way is that because we had to do it from scratch pretty much, do the equations and all this calculus stuff, we gain a deeper understanding of how it works than if we just use a library. So I think that's the biggest advantage of learning this thing, because then you go to a library and then you start seeing all these nodes, pre-made nodes, and then you know what they do. And you don't need to know the code, you don't need to think about dimensions, but you just stack them and you know what they do very clearly. So I think that's the main motivation behind TDNeuron. And of course, yeah, let me show you some of the stuff that we were working on. We're working on an interface to make all this process that Tim was showing, because now you have to jump here, jump there, and put a table. It's very uncomfortable. So we're working on an interface so that you can do it with nodes. So it will look, at the moment it looks a little bit like this. So you see here we have the layers, linear activation. We're working also with convolution and some other cost functions. And then what you will do, you just drop it. And then you create an activation function. When you click here, it's going to give you the information for that one. So you could change here the amount of neurons. Let's say we want 32 for this guy. And here you can change it to be the activation function you want, so tanh. And then you can draw up another one. No, let's drop this one. Another activation. And then you can also connect things. So you can connect it to this. And then this will be your model. So what you will do then is just press generate. And it will spit out a table that is the table that Tim showed. And with that table, you can just press in the other patch, generate, and it will make the network for you. So you don't have to do all these crazy things that Tim is now trying to solve. This, we want to extend it because there's a very interesting possibility when you start doing generative adversarial networks that you can have different streams of data. So for example, if you have this, like I had before, but you could also have suddenly this. This should work already with deleting and connecting. So now there's a bifurcation. And you can have two networks working at the same time. And then you will have an extra operator in between here to create the adversarial part of it. But in principle, this already works. It's just a little bit hard. We have not decided yet what's the best architecture to give it out yet. But this is what we want to achieve, that you can use it like this, that you can also play. Because most of this, like we said, comes from really just doing this. I mean, you have to put some things together. Sometimes it works. You don't know why, but it does. And hopefully with this kind of tools, it will be easier to find out, you know. Then let me see something else to show. You have it already? Okay. Yeah, there's so much experiments we did. And we are trying to work also in these tutorials that we sent. So please, if you have some suggestions how it was written, none of us is a native English speaker. So for sure there's some horrible stuff there. So that could be one way, yeah, one way that you can help directly. Also, if you want afterwards the workshop, meet with us for a beer or something. We would love to see if you have recommendations. If you know math, because we're not mathematicians, if you know more math than we and we did some mistake, also please let us know. All that stuff is really helpful for us. And finally, he has what he wanted to show. If he finds a socket. In TDNeuron? What do you mean? Oh, like speech or sound? Yeah. No, not yet, no. It's all just, for now, images.
So I managed to find it, or to fix it. Okay. What I wanted to show is like the same autoencoder, but now with bananas. And if we start, we view this. So this is the prediction. Right now the prediction is all empty, and it takes the mean of the data, the average of all the images I took in the beginning. So you have like this zero centering Darien was telling about. We're doing this now with an image. So taking the average of all the images and then scale it down to there, so it's all around 0. And if we now train it without pause, first reload it. Okay. Okay, the learning rate is way too high because, as you can see, it makes really garbage kind of images. Maybe change it a little bit to less, and then now we start all over. So as you can see now, it tries to make the same kind of images as we put in. So this is our input. Now it tries to recreate those images by first scaling down all the information into 2 floats and then trying to recreate it again. So what it does, it's try to find the common things about the bananas. Like those guys are those and those, and they look like each other, and that's why the image, the output image looks like it. If you train it more and more and more, it will get closer to the images, but it also depends on because we scale it down, the information, it has to make compromises, what to remember and what not, what to connect to what's important about a banana. Like, is it the shape of it, or this here, for example. In this case, the background is a little bit bluish, and you see here that guy is also bluish, and here they take almost the same image because it thinks like, it looks like the same banana. Now, if this continues and continues, here it shows already a little bit of a banana. But if we now load the guy, should not train it. So this is after like half an hour of training. And as you can see, it's still not all of them, but a couple of them look already like bananas. And what you can do now is this whole model ends up to be here. Okay, in this case it's 8. It makes it as small as 8 floats, 8 different values. And what you can do now is delete all the top stuff of the model and use only from here to downwards. And then with 8 floats, you can create bananas. So similar what we did with the digits. And so now we have just, again, one sample. This is the one. And if you change those values, okay, it all doesn't look like bananas because we only trained it on 181. it would be nice if we have 60,000 of them, and then you get closer to real bananas. This is like, okay, it takes the yellowish color, but that's it, you know. It's really hard to find. Ah, there's a banana. So this stuff. So this is kind of the research where we're playing around with now. And yeah. No, that's about it, I think, huh?
All right, yeah. So, so we made this tool called device recorder, and the device recorder allows you to record a device. So you can choose. Now we have two types of devices, which is what we had at home. So I had a Mayo controller. I don't know if you're familiar with it. It's like an electromyographic sensor, and Tim has this lip motion. So what you can do is you can have the lip, and it will give you your hand, for example. Can it do that as well? So here you have all your data, and what you can do is you can go into here, choose not live, but you can go to the recorder. There's an amount of parameters here that allow you to select different classes. So for example, let's say I want to do, we're going to begin with 0. I'm going to do 3 different classes. And this is the amount of samples that you're going to take from each class. You want each sample to be a little tiny bit different, because like what we saw before with the numbers, if you have slightly different numbers that are not into the training set, you will not be able to recognize all the possible numbers. So let's say we want to train this gesture, then what you should do is to train it like this and do slightly different positions maybe, so you can recognize more variety. So what you can do at this point is I'm going to do 300 samples of those, and I'm going to have 3 different classes. Then you can start the recording, and then you can do this. So I start recording this gesture, I move it slightly, then second gesture, maybe I'm going to do number 3. So it's going to tell me when it's done. Ah, because it should be, oh yeah, there. And then I should be here again, now I do 3. It records it. It's 4, kind of. My hand is a bit fucked up. Okay, and then 5. So always, yeah, make sure to do slightly different variations. Then you have it. You have those 3 things. Oh, wow, what is doing 4 now? Left hand, whatever. And as you see, it's populating this menu. So this menu is populated for you. You don't need to think about it. And once it's done, you have all your data in a folder in the recorder. So it saves everything here, saved, and it saves it by device. So it saves it on the device name, and then you can create subfolders. So this is what we did. We did all these different data sets for the workshop. And you can create your own in this way. Once you create your own within TDNeuron, I think there is already a mechanism to import it in. Yeah, well, this is a bit tricky, though, because the data importing, we still don't find a universal way to handle all data, because every data type is different. So you do need to process a little bit your data yourself. So what I mean is this. Let's say you have those models. You go to TDNeuron, and here in the inputs, you can choose your inputs. So let's say device recorder is the device recorder I just showed you. And if you chose that, you will have here the option to select the data types from each device. So now I did some lip motion recordings, and it will look automatically to the path saved and the deep motion folder that I showed before. So meaning it will be saved and recorder, saved, and the lip motion recorder thing. Here we have this approach that seems to be the most comfortable for now, which is a replicator that is going to grab all the channels that you did. In this case, I did 4 recordings, right? I did these 3 on the left hand. So it will grab those, and I will make copies from them. However, there is some things that change from data to data. For example, the lip motion requires us to, what you were asking before, to get rid of some data that is not important for us. Because if you have a lot of data, not all of those data is meaningful for the target. So you have to clean it up. So if you see here, some things are being cleaned up. Direction, whatever this is, the hand rotation, and so on. And then this you have to do yourself, because you cannot really, I mean, you have to find it for yourself. And for the Mayo, for example, I ended up finding out that everything was kind of irrelevant. The only thing that mattered in the Mayo, oh, I'm in the wrong one? Oh yeah, sorry, yeah. Sorry, let me change to Mayo. So that's the other controller we have. And now I have my inputs, but I find out that the gyroscope and the acceleration is not meaningful. So I got rid of those, and I just keep the sensors and the orientation. So this is something you have to play with and find out. But hopefully this tool allows you to play with your devices at home as well and make your own data sets. That's the fun part, and then you can learn how it works. Yeah, and of course this is just like a very small part of all machine learning. You can also do things with continuous signals, because now we're just looking at some sample in space. But you can also do it with audio, for example, and resynthesize something. And this is something that, yeah, the principles remain the same. The structure is a little bit different further down the line. But if you know these things, then it makes so much more sense when you see, like I said before, a library. Then you know what these things mean, and you know how to play with them. And you can search nice, you have better ideas on how to use this creatively. And I think that's what we all want to do, more or less with touch, to be creative with stuff. And yeah, I mean, that was the point of it. So that's it. I hope you had fun. Maybe it was a bit too heavy, but hopefully not. All right.